Chapter 2 is where we're at now in the textbook. Chapter 2 is chemistry. A lot of you probably say, oh, you know, I know chemistry. I took Mr. Vaughn's or Miss Park or Miss Roberts' class. I got this. And you probably do. And that's good news for you with respect to this unit. Chapters 1, 2, and 3 will be the first examination. We'll be over those chapters. Some classes in some schools don't even teach this stuff in the AP biology curriculum. They're like, oh, students know all that. So I did that once, and I found that students really struggled if they didn't redo chapter 2. So we're going to look at it. It should all be review. I would ordinarily give you a handout, and I wish maybe I could give this to you in class before you take a look at this lecture. Just know one of the important things that you're going to need here is a periodic table. Of course, I just had it with my finger, and I lost it. It's in the back of your textbook. Sometimes it's better to be lucky than good. B1, there's a periodic table here. If you were in class, I would be motioning to my periodic table that's over there with a laser pointer and everything, but we'll refer back to this and maybe that little handout also a couple of times. There are some bits of information that I want you to get off of the Google Classroom here before you start chapter 2. Number one is that we're not going to go over any of these learning targets. We're not going to pause or have you turn in anything with respect to that. You will, however, have to turn in some written answers to concept check questions. What I mean by that is, here I am in chapter 32. Right here, concept check questions. In each chapter, you'll see these multiple times. And what I want you to do is I want you to stop after that, say page and a half of instruction from the book, and write down answers to these questions. They're supposed to check your comprehension midway through the chapter. The answers are in the back of the book. I want you to cheat. Go look, please. However, I do want you to try on your own first. I think it's always beneficial to have the answers, especially when you're home alone. Not with your teacher, for instance, but try first, and I'll give you credit for completion of those. I don't really like the stuff on electron orbitals, the D, the F, the P orbital stuff I remember from college. It's not applicable to this class. Make sure to do the test your understanding at the end of the guide. There's some questions there, and it's just, again, another comprehension check. I will give you credit for that. Do that for every single chapter, please. And then I do want you to watch a few videos from my friend Mr. Anderson and fill out the podcast and website worksheet. I will have explained what that is to you. Remember, we're going from small to big. We got to start small, and there's no smaller place to start than atoms. So remember, 1 centimeter across, about the width of your pinky finger, 100 million atoms make up this space, and they are in there. And you can imagine that's 100 million atoms, and they're infinitesimally small, like I guess side to side. You can imagine how many make up your body. It's absolutely crazy. So let's start with a movie.
Time, space, and matter. Matter seems like a good place to begin. The solidity of the world seems totally indisputable. As a fixed thing that you can see and touch, your body is also reassuringly solid. But beginning with Einstein, modern physics has assured us that this solidity is a mirage. After all, the body is made up of atoms. These atoms are particles that are whirling at lightning speeds around huge empty spaces. And the particles aren't material objects. They're fluctuations of energy and information in a huge void of energy.
Okay, what's going on here? Let's imagine that this is the nucleus of one atom. Tell yourself where you think the first electron orbital, that first inner shell of electron would be. This is the size of the nucleus. The answer is Eaglevale. And what's between here and Eaglevale? Cars, Bears, Burger King, right? There's a lot of space between here and Eaglevale, and the electrons are so small that they don't even have any mass. So this is an atom, let's say a carbon atom or a hydrogen atom that's inside your body. Nucleus, first electron orbital, Eaglevale. What is in between them? The answer is empty space. In fact, every atom that exists in nature is made up of 99.99999% empty space. So, if you're made up of atoms, what are you mostly made up of? Empty space. And the 0.00000001% of you that is actually matter isn't really there either. Let me show you what I'm talking about. Einstein taught us that if E equals mc squared, right? And what is m? Stands for mass, or matter is anything that takes up mass, has mass and takes up space. This is just a number. This is the speed of light squared. You can imagine that that's a pretty big number once you square it. And this is energy. So that amount of matter that you are, that 0.0000001% of you that is actually matter isn't there, because what is matter? It's just energy. So let's review here. You're not there, but what is there isn't really there because it's just energy. In fact, I once read that if you were to spontaneously combust and all of your atoms were to split open, so much energy would be released, like when they split the atomic uranium and plutonium bombs to end the World War II over Japan. So much energy is released that if a person was to spontaneously combust and all of the atoms were to split open, you would flatten the state of Colorado. It would be a smoldering ruin. This pen could flatten all of Edwards if all of the atoms were split here. There's so much energy in that so tiny space. So think about it. You weigh, when you step on a scale, so your mass is your weight in the influence of gravity, right? So it's 140 pounds or whatever. So think about that. You weigh 140 pounds, and that is such a small fraction of a percentage of actually what you could potentially weigh. But I'm going to tell you, if you took all the matter in your body and you condensed it down, it would be tinier than the head of a pin. So think about a pin head and how much that weighs, 140 pounds. So you are simultaneously nothing, sorry to break it to you, but everything. Because what else is there? I mean, look around, hug your family, pet your dog, jump on your bed. What else is there? There's just the things that we have around us. And it's all energy. You ever heard people say, well, he's a really nice guy, but I'm just not into him? And maybe that's because all that individual is just these vibrating energy waves. And that's all you are either. And that's when people say spread the love or spread positive energy. It is all about energy. It's the crazy thing. Sorry you're not here. None of this matters. A for everyone. Semester's over. Let's finish the movie, sorry.
Information. If you could see the body as it really is, you'd see that 99.9999% of it is mostly empty space. And the 0.00001% of it, which you see as matter, is also empty space. The matter is just an illusion, an artifact of our perceptual experiences. As you sift through this very solid-looking material body, you only have to go so far before you end up with a handful of nothing. This is a scientific fact. The question is, what is this nothingness? What is this empty space that makes up everything in existence? Because it's very clear that the basic raw material of the universe is that it's not material. The essential stuff of the universe is non-stuff. Because an atom, which is the basic unit of matter, is not really a solid entity. It's a void. But is this void an emptiness? Or could it be the womb of creation itself? Could it be the source of life itself? Is this non-stuff, non-matter that makes up the entire universe just emptiness? Or is it thinking non-stuff, thinking non-matter, that curves back within its own self and creates everything in existence, from matter to energy to time to space? As you dissect through the body, the various layers of organs, tissues, cells, molecules, and atoms peel away until at the subatomic realm, all that remains are bundles of energy vibrations. The nerve receptors in the body are switching stations that can take energy vibrations and turn them into touch, sight, sound, and so on.
Why? Why then, if someone jumps out of a building and hits the cement, why do they die? Well, if they're not here, and most of them is just empty space, same with the street, the answer is the electron repulsion. Remember, electrons are negatively charged, and those electrons will repel each other. So it's the same as your clothes. You're not really wearing your shirt, or you're not really sitting in that chair. You're levitating over the chair because of the negative repulsion. You never really ever touch the chair, or touch your shirt, or touch another person. So let's go. Sorry, we can go down that rabbit hole all day. Let's draw helium in just a moment, but I want to call your attention to this up here, this C12-6. Remind yourself, what does the 6 stand for? 6 is the atomic number. What does that mean? Well, I remember 8 man. Atomic number is the number of protons. It's the same as the number of electrons in any atom. How about this bigger number? What does this number stand for? This is the atomic mass. The larger number is the mass of the atom. How you get that is you subtract the atomic number from the mass number, and that will tell you the number of neutrons. Remember, neutrons are neutral. They're things that exist in the nucleus of atoms. Protons are in there too, and then electrons are what spins around the outside. You can look at the periodic table. I guess it's probably easier for me just to hold this thing. So, how is this organized? Well, as you go across here, it tells you how many electrons there are in the outermost valence shell of that atom. So how many do hydrogen have in its outermost shell? 1, and then 2. This also tells us in the first row here that there can only be 2. Go ahead and draw this also. There can only be 2 electrons in this outermost shell. 2 electrons. Now, because atoms are electrically neutral, what that tells us is that there's 2 protons in the nucleus. And if I take the atomic mass, so let me see what that is for helium, it's 4. So it's right here, it's 4. So if I do 4 minus 2, which is the atomic number, I know that because there's 2 electrons, 2 protons, that's the atomic number. So 4 minus 2 tells me how many neutrons are in here, and that's going to be 2 neutrons. This is a negative, or sorry, this is a neutral charge. I just put a 0 with a slash through it. Well, if we look at the next row down, so we see down here lithium, beryllium, and so on, what does this tell us? If you look at lithium, what does the 3 mean? Well, the 3 is the atomic number. That means that it has 3 protons, 3 electrons. What is the significance of being in the second row down with lithium? Well, that tells us there's 2 electron shells. All of these guys across in the second row have 2 electron shells. Beryllium's going to have 2 electrons in its outermost shell. Boron's going to have 3, carbon's going to have 4, and so on. So you could change this out. So if I erase the letters He there and write carbon here, I know that carbon's going to have 2 shells. It's in the second row down. 4th column over, that's going to tell me that in this outermost shell, it's going to have 4 electrons. But because the electrons have to equal the protons, and that equals the atomic number, how many protons is carbon going to have? Well, it has to be electrically neutral. if I look here, you'll see a number, and with carbon, it's 12. I think it's like 12.001. Now, that's not a whole number. If I was to do the math, 12.001 minus 6 equals the number of neutrons in here. You're not going to have 6.001 neutrons. For this isotope of carbon, that just tells me that it has 6 neutrons. Now, there are different isotopes of carbon. There's carbon-13 that exists out in nature. That would give us 7 neutrons. We have carbon-14 that exists out in nature. But these are very rare, and that's why the average, so that what you see with the atomic mass number is always an average number of the number of neutrons that are out there in different isotopes of that atom in nature. In this example, it's carbon. Make sure that you get this down, how this is organized. I'm going to tell you, your book's going to talk about schnapps. If I hear you muttering schnapps during the test, I'll be okay with that, because what they're saying here is that 96 or 98% of all the atoms that exist in living things are made up of these 6 atoms. Periodic table has like 111 elements. I think 92 are naturally occurring, and 19 or something have only been ever isolated in a lab, like for a millisecond. And then they have these weird names like Berkeleyinium and Lawrencenium, like Lawrence Livermore Labs, which is out in the Bay Area next to Berkeley. So they get to name them, Americanium or whatever. But those things don't really exist out in nature. And more specifically, these are the characters that you're going to really need to focus on and know how to draw and know everything about them. We're going to start to make macromolecules where we start to put all these together.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? To understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? It's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you can see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class, where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and we're searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it's empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of the nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, you would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium. And now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
It's crazy. That's why I want you to think of a 1 foot box, 1 foot by 1 foot. And if you crushed a car and got it into that 1 foot by 1 foot box, but you did that to 6 billion cars and they all got in there, that's how dense nuclei are. And that's why there's tons of energy in here. That's this Einstein's equation. It's pretty crazy. Well, I know Saturday night's coming up. I have 2 little songs for you to get you excited about the periodic table. Please, please, when you have friends in the backseat of your car, these are on the Google Classroom, just crank up your stereo and show your friends what's really going on. Here's the first.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, and beryllium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, titanium, and indium, and gallium, and iodine, and thorium, and thulium, and...
Yeah, I had a student that had memorized this and sang it to me a few years ago. It's awesome. Love bio nerds.
Yeah, they're gonna be fooling around. And first, take away for oxygen when I'm headed into the booth with aluminum. You shoot hitting oil, my pants loose. Man's open up the llama and take their diamond up for speed. Equivalent with mercury burning your mind. And it's up in the laboratory. Now lithium in your iPod. Service suckers up like I hot. Yeah, pancakes, you rappers can't hate. I'm MCing that iridium. You suck beryllium. Worms and you smaller than living on the bearing as the rest of the king. I got them all the baby. Give you magnesium or something that's concentrated. Vitamins and minerals. Again, I ain't the minerals. And I really see the mental within a little bit of me. That's simply and these rappers all fraud. Show them the link and everything shit off.
Okay, it's pretty awesome. Done here. Make sure that you get this, how the periodic table is organized, what it all means as far as electrons, how many electron orbitals, what do the rows mean, what do the columns mean. Be sure to be able to draw this because it's only going to get harder when we start to put these together at the end of chapter 2 with bonding, covalent, ionic, hydrogen bonding, these van der Waals interactions that we'll talk about. Make sure you get this all done. If you have any questions, let me know. And I'm going to ask you, when you think about chemistry in high school classrooms, what do you think about? Blowing stuff up, right? So here we go. Kids always ask me, hey, when are we going to blow stuff up? Not in this class. Want to watch some more high school chemistry classroom fails?
Happens that that side needs to be connected to ground or negative.
I don't think this witch's head is fireproof.
I don't think so.
See.
Okay, we can work the whole day.
And up goes the $20 bill, so you think. Right, and it continues under that.
Yay. Okay. Thanks, guys. See you soon.